Okay, great. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you, Lord, that you loved us so much that you died for us and came to earth and died sacrificially for us. We just repent and accept you in our heart. We know we have forgiveness of sins. And Lord, we thank you for your many blessings to us this day. Let's pray to be with us, class. Help us to glorify you, what we do here this day, Lord. You know I pray. Amen. Okay, so last time I showed you the general definition of the derivative, kind of briefly. And so let me just kind of give you a brief synopsis of what that's about. So here's the intuition. Just in brief, if you have a function and it's some function from, say, Rn to Rm, then to say f is differentiable in the Fréchet sense means, well, at a point, let's say A. Now, I guess I used P last time. I put a vector on it. P in the domain of F means that basically you can write f of, f of x vector as equal to, forget my vectors. Vector. Okay. If f of p plus, well, the Jacobian of f at the point p times the times this vector x minus p, and then plus some remainder term. And I mean, essentially, if the function is differentiable at the point p, it just really means that you can essentially discard this. This goes to 0 as what? As x goes to p. In the technical sense that I gave you last class, I mean, there's this limit, the Fréchet quotient, it goes to 0. That's essentially just capturing this notion that the remainder becomes negligible if you're close enough to the point. All right, that's all. In this case, you can talk about something, you would say that the function is differentiable. You'd also say that there's some kind of like tangent plane. But I have the definition in my notes, even the definition, like the notion of a tangent plane for something like this. But I don't really care about that generality in here, so I'm just going to let you read it. I'm not going to write it down even. But this is what I mean when I say differentiable. So, let's look at a specific application of that. How about functions of two variables? So, in particular, think about a function going from R2 to R, right? Then what? So what I'm saying is if it's differentiable at, let's say, P, and let's let P be A comma B, all right? Then we have f of x comma y equal to f of a comma b plus, well, what's the Jacobian of f look like? Let me remind you, the Jacobian f in general, I told you the Jacobian of f was something like, we do partial f, partial x1, partial f, partial xn. I calculated one for you last time. But there's another way to look at this. If you look at the formulas we have, you can also look at the Jacobian as a stack of gradient vectors. So it's the gradient. It's the gradient of the first component function written as a row. So I've put what's called the transpose here, since my gradient is a column vector. Gradient of the mth one, like that. So what I'm trying to say is, in this case, the Jacobian of this function at the point a comma b, it's actually just this row vector. It's partial f partial x at the point AB, comma, partial f partial y at the point A, comma, B. So, when I write this expression, in this particular case, I just have, basically the gradient of f at the point AB dotted with this difference vector, x minus a, comma, y minus b, like so. Plus a little remainder term, some remainder term. And that remainder term becomes small as x approaches the point, x comma y approaches the point A, comma B. Provided what? Provided that the function's actually differentiable. But there's a more geometric way I can capture this notion of differentiability. What does it really mean? I mean, what does that mean about the graph? What does it mean about the graph of the function? To suppose that there's some remainder term and it goes to 0. I mean, geometrically, what this is really saying is that if the function is differentiable, then the graph of the function is well approximated by the tangent plane close to the point of tangency. Now, what's the equation of the tangent plane? If we have z equals f of xy as a graph in 3 dimensions, right? The tangent plane, the equation of the tangent plane is just given by these terms right here. So z equals to f of a comma b plus f sub x, a comma b, times x minus a plus f sub y at the point a comma b times y minus b. This, folks, right here is the equation of the tangent plane to the surface. Now, that exists and it well approximates the surface if the function's differentiable at the point. Or again, this differentiability is a technical condition as quantified by that Fouché quotient I gave you last class. But there are some easier to understand conditions. There's like a little theorem that we prove in advanced calculus. The theorem says as follows. Just a little theorem. If f is continuously differentiable, that implies that z equals to f of x comma y, let's say at the point a comma b. Then that says that z equals f of x comma y has nice tangent plane at the point a comma b. In other words, continuous differentiability implies differentiability. What was continuous differentiability? That was an easier thing to understand. That just was talking about partial derivatives of f. That means like partial f partial x and partial f partial y are themselves continuous functions. So let's see here. Let's look at an example then. How about this? Let f of x comma y equals to x squared plus y squared minus x. Find equation of tangent plane at some point. Let's see, where do you want to find it? I could either characterize the tangent plane by a pair in the domain or by a triple that's actually the graph, right? How about 1, 2, and then what would the z-coordinate be if it's on the graph? Four? Okay. Silence! They never listen to me. All right, I tried. Let's see here. So what you do, it's very simple. If you believe me at least. I calculate fx. What do I get? I get 2x minus 1. I calculate fy. I get 2y, right? So Therefore, fx at the point 1, 2 is what? Plug in x equals to, what I get? 2 times 1, 2 minus 1, right? And over here, I get what? 4, okay. Thus, z equals to 4 plus 1 times x minus 1 plus 4 times y minus 2. That right there, folks, is the equation of the tangent plane to that surface at that point. Here, let me do another example. How about this? F of x comma y equals to 3 minus x squared minus y squared. I want to find the tangent plane at 0, 0. So let's see here, gradient of f. Sorry, let me problem find the tangent plane at 0, 0. This time I'm characterizing where we're looking for the plane by the domain value. All right? So what do we have? We've got the gradient of f is what? It's minus 2x minus 2y. So if I calculate the gradient of f at the point 0, 0, what do I get? Yeah, I get 0, 0. So thus z is equal to, let's see, z should be equal to f of 0, 0 plus the gradient of f at 0, 0 dotted with x minus 0, y minus 0, which is just xy. That's the equation of the tangent plane, but what does that work out to? Not 0. I mean, you're right, this piece is 0. 3. Does that make sense? In fact, it does. I can kind of give you a picture of what's going on. I didn't want to try to draw a picture over here. Seems unpleasant. But this one's not too bad. So basically, this is a what? This is a paraboloid that opens down, right? And its top is, here. So I don't know. Where's the where's the y-axis? Where's the x-axis? Whatever. The point is, the tangent plane is just z equals to 3. It's a horizontal plane, right? It just rests atop this paraboloid. See that? Okay. Now, I just have suggested that the tangent plane should basically be, my viewpoint today that I've advocated so far could be put into these words. I'm saying that the tangent plane should be the graph of the linearization of the function, right? The tangent line is the graph of the linearization of a function of one variable, right? You look for the best linear approximation to the function. The graph of that thing is what we call the tangent line. So here I'm advocating the view that the tangent plane, it's the graph of the best linear approximation to a function of two variables. That make sense? What's another way you could look at a tangent plane? Like how else would you try to describe geometrically what a tangent plane was? If you thought about a function of two variables, graph in 3 dimensions, how else would you think about a tangent plane? Any ideas? So I want to look at another approach to motivating the tangent plane equation, okay? At the moment, I just dropped it from the sky, essentially, right? I just told you what it was, and then I showed you here's how to calculate with it, right? So if you accept on authority that this is the equation of the tangent plane, then we're done, but I think you should want to understand things more deeply than that, right? What's another way you could look at a tangent plane? Let me draw, yeah. Oh, nope, that was just adjusting here. Yeah.
Is it kind of like every single tangent vector?
I like that. So if I have something like this, here's my silly surface, right? So this would be the graph, right? Z equals f of xy. So we're still in the world of graphs, let's say. I mean, you could ask the question, well, how do you define a tangent plane to like a level surface, right? Or how do you define a tangent plane to a parametrized surface in R3? Those would be other questions that we'll ask on other days. But I like your suggestion here. So we look at the point, and you're saying look at all possible tangent vectors there. Now what would you mean then? Tangent to what?
To the point.
To the point. In what sense? How do you? To the surface, but that's the thing is that's what we're trying to define. So I need something else, something primary that you already know about tangents of. I'm not disagreeing. They only cross the graph at one point, yeah. Yeah, but how are you getting the vectors that are going in every direction? What are you using to find those vectors that you're coming up with? What concept? Yeah. No, not what I'm fishing for. What have we studied already in this course? Dot products, also true. Not what I'm looking for. How about maybe? And if you already said it, I'm sorry, I didn't hear you. How about one of these? How about a curve? Right? If we study curves that lie on the surface, those must reveal something about the geometry. We already know how to find tangents to curves, right? So what I'm advocating is that you think about all possible curves. All possible curves through the point, right? And then you just think about the tangent vector at the point for those curves. And then if you can glue all those tangent vectors together in some sort of meaningful way as to assemble a plane, right? That should mean that the tangent plane exists, and it's formed by the union, the locus of all those tangent vectors to all those curves. Does that make sense? And we're not assuming the point there either, right? Because we have a notion of tangent vector from before in the course. We know how to differentiate a curve and, put those together. So here's my horrible picture of that. Now, there's a problem then. I can't draw it worth anything. Anyway, you get the idea. So all possible tangent vectors. So what does it mean then for a curve to be on the surface? How do we describe curves in 3 dimensions? What's the tool we use to do that? By the way, I'm breaking from the notes a little bit right here. I'm going to come back to this general differentiation from time to time as it makes more sense, as you gain more experience about the basics. Then we'll dip back. We'll come back to here from time to time to connect with that general picture. But it occurs to me, I think it'd make more sense to you if I first show you a little bit more about just garden variety partial differentiation. So it's, we're on the path to doing that. Again, my question: how to characterize a path falling on the graph z equals to f of xy. And we want to focus, we're particularly interested on a particular point. So we want to focus on a point P, which again we'll say is A comma B, all right? All right, this marker's dead to me. Oh, yeah, there's a roof. Let's see here. Now you're awake. Okay, so how do we, first of all, path, what should we do? I say we should look at the mapping T maps to r of t, right? So you've got x as a function of time, you've got y as a function of time. I mean, that's how we think about paths. Oh, hey. Phooey. I guess I need. Oh. Curses. Well. Trying to think of the nice way to say it here. That's what I get for using graphs. I should have used something else. Oh well. Fine. So what do we have to be able to say? I mean, that's not. I want a path in 3 dimensions too, right? So I also need what? Yeah. So what does it mean for that path to lie on the graph? This is actually way easier if we were looking at level curves, as we'll see in a later lecture. That's what's bothering me, if you're wondering. Okay, so if I need that z of t, right, is equal to what? Yeah, f of what? F of x of t, right? Y of t. So that would be what would be required for a path to lie on the graph. Something like that. Let's see here. For example, excuse me. Going back to our example, we had what? We had z equals to, what was it? 3 minus x squared minus y squared. So if you wanted a path that went through the point where we found the tangent, right? You wanted a path through this top point. I mean, there's lots of different paths, right? But what's one? How about if I put x equal to t? Can I get away with that? And if y equals to t, can I get away with that? I think I can. Z equals to what? Yeah. 3 minus t squared, minus 2t squared. You got it, you got it. So if I think of these collectively as the path r of t, t, 3 minus 2t squared, right? How can you think of those in the bigger picture of the graph here? You can envision those, right, as the if you look at the xy axis here, you can see those actually. My picture's not very good. My curve actually should look more kind of like, I don't know if I can draw it very good, but this is the curve y equals x in the domain, right? If you have x equals to t, y equals to t, that's the line y equals x. So basically you're feeding y equals to x into the graph, into the function. You know, this is the function f of x, y. And so you can think of it this way. Down here, I've got this basically, here's y equals x, which is also equal to t. And then on the graph, that's giving you, this curve, which goes through the point of tangency we just studied. See? And then it would keep going on the backside too, right? Corresponding to the rest of the line y equals x, which is, I don't know, it's hard to draw in 3 dimensions, but it's this curve, right? And you can calculate the tangent line. Now I got to be careful, right? I got to choose the right parameter value to find the tangent vector, but it should be something like this, right? That should be r prime of 0. I'm not sure about the direction of it, but something like that. So can we calculate it? What's r prime of 0? It's what? 1, 1, 0. Is that vector tangent to the plane we found? Over here? Oh, sorry, over here. Z equals 3, right? What's the normal vector? 0, 0, 1, right? Is this perpendicular to the tangent vector to the sample curve we just looked at? It is. Yes. And you can try any other possible curve that lies on the graph and goes through that point, and you will also find that those are perpendicular to that normal we found. There's two different ways of approaching it, right? We can use this, at the moment, not entirely understood formula that I gave you, right? Or we can study curves that go through a point and find the vectors that actually lie in the tangent plane if you want. Right?
Tangent and a normal, can't you just find the binormal and then parameterize the plane in terms of those?
Well, here, in order to find that, with just what I have here, I would need to look at another curve and find another tangent vector. Then I could take the cross product of those two tangent vectors, and that would give me the normal vector, for example. But this isn't, what's just here is not quite enough information to figure out the normal vector. I mean, the formula I wrote down here and have erased and have used over there is fantastically simple, right? You just calculate partial derivatives, plug in the point, done. Tangent plane. It's awesome. I mean, it's simple. But why is that the formula for the tangent plane is still a question that we need to understand more deeply. Okay, so in order to really answer that question properly, we need a thorough understanding of what's called the chain rule, all right? It's probably worthwhile for me to start diving into those examples then. And so once we have a good understanding of the chain rule, I'm going to come back to this discussion of what the tangent plane is, and we'll try to look at it more deeply. Eventually, we'll understand how to calculate the tangent plane for a level surface, for a graph, or for a parameterization of the surface. Our three different views of how to understand surfaces, right? At the moment, I've only shown you, and haven't even motivated, really, how to find the equation for the tangent plane, right? For a graph. But we have two other viewpoints that we can take. So the chain rule. What if you have, let me begin with an example here. What if I have f of xy equals to, say, x squared plus the cosine of y. And I also have a path, let's say r of t, equal to t squared. So the question is, how would you differentiate something like f of r of t? What if you have the composition of a function of two variables with a path? How does that differentiation work? So the chain rule is simply this, guys. It's you write the gradient of f, you plug in the inside function, which here is the path r of t, and then you take the dot product with dr dt. That's the chain rule for this context. So let's see here. What's that look like? Let me write it out in more detail. So what we're looking here actually is partial f, partial x, at the point r of t, comma, partial f, partial y, at the point r of t. That vector dotted with, what's dr dt? Well, it's dx dt, dy dt, right? And so if you actually take that dot product, what you have is this. You've got partial f, partial x dx dt, plus partial f, partial y, dy dt. But it's useful to understand this chain rule as it relates to the gradient vector, as well as the formula I wrote at the end. Now, what I write here is general, right? Now let's apply it to the, so I mean, let me just, this, what I write right here is, you know, that's the general identity. We could prove it, right? How does that work out for that example there? So d dx, x, listen to me, d dt of f of t comma t squared. So I'm saying it's partial f partial x, right? I thought it was an ant. What's partial f partial x? It's 2x, right? So I have 2x times dx dt minus the sine of y dy dt. But what's dx dt? What's dy dt here? It's what do you got? 1 and 2t. So 2x minus the sine of y times 2t. Now, am I done? It depends on the instructions. If I say that you can leave the answer in terms of the intermediate variables, then this would be an okay answer. But if I say you must express the answer in terms of the independent variable, then we're not done yet, right? I have to, what is x equal to? What's y equal to? X is t, and y is t squared here. All right? So I have 2t minus 2t sine of t squared. There it is. Questions? Again, I'm going to keep coming back to this problem of the tangent plane as we go on. And this curved viewpoint is something we're going to keep using. Any questions? I mean, usually somebody asks me at this point, why do I need the chain rule? I could just plug in time and differentiate, right? Like, what is this? It's t squared, right? Plus the cosine of what? T squared, which gives you that. So why use the chain rule? I mean, here it's kind of simple. I mean, but there are many examples where the chain rule is the only way you have to do it. Let's see here if I can give you another example. Suppose we have gamma of t is a vector, is a path. It's x of t, y of t, z of t, right? And you have f of gamma of t is equal to some constant, let's say c. So here, f is a function from R3 to R, all right? This example will answer the question I just begged, why you need to know the chain rule. Sometimes you don't have even formulas for the thing you're composing with, but you can still do the chain rule. So the chain rule in this case, d dt of f of gamma of t, it's the same chain rule. Now we have three intermediate variables. The variables in the middle are the intermediate variables. So in this first example, the intermediate variables were x and y. I didn't even give a name to the, I suppose you could say the dependent variable here would be z if I had written z equals to f, right? The independent variable was t. There was just one of them. So here the intermediate variables will be x, y, z. The independent variable is just t. And so the chain rule is this. It's the gradient of f at the curve, gamma of t, dotted with the gamma dt. Now what's that? What's that equal to? Well, I told you that the curve, when it's plugged into this function f, it gives you back a constant, right? So what's the derivative of a constant? 0. Yeah. Okay, so now I can write these kinds of formulas out here, but let me not do that to distract from the main point. What does this say about this vector and this vector? These are what? Their dot products are 0. They're perpendicular, right? Okay. What does it mean to have f of x, y, z equals to a constant? What is that? Here, how about this one? F of x, y, z equal to x plus y plus, how about x plus 2y plus 3z? Equals to whatever constant you like. What do you guys want? 64? Okay, very good. Always interesting. Definitely, you have a future as a random number generator. Future is safe. So here, if I had a curve, right, that worked like that, like for example, what? I don't know. I mean, you can all kinds of examples of curves that lie on that plane. What do you want? How about 2t minus t and 64 over 3? Is that weird enough for you? So that curve, if you plug it in, plug that curve into the equation, you get back 64, right? That's a curve that's on the plane. What this calculation right above says is that the gradient to the level function, right, is perpendicular to what? What is the significance of f of gamma of t equal to c? What does this mean geometrically? What is this? What's it say? It says that the mapping t maps to gamma of t is a curve on the level surface, right? And if I plug in the parameterization of the path into the level function, I get back the level. That means that that path actually lies on the level surface. For example, this silly path lies on that plane. And you can easily calculate that the gradient of f, by the way, it's a shame. It's a shame that I didn't do this example the other day. Like, what's the gradient to a level surface? How about we look at a plane, right? If you take the plane ax plus by plus cz equal to d, what's the gradient of that? It's abc, which is the normal vector. Right? For shame, I did not do that example the other day. Duh. Here it is. So the normal to the plane is the gradient to the function, right? 1, 2, 3. How about gamma prime? What's gamma prime of t? 2 minus 1, 0. And that's true for all time. Because the tangent vector, that curve that lies in the plane, it doesn't matter what time you're looking at, it's always perpendicular. So if I had a more complicated thing than a plane, you know, if I had some honest to goodness level surface that had some kind of complicated shape, I don't know, and I had a like that, and I had some curve that was on the surface. If you look at the tangent vector to the curve like this, the geometry is that those tangent vectors, they're always perpendicular to the gradient. So the gradient is always pointing. So if I have, this is f equals to a constant, these are the gradient of f at those different points. The gradient vector field points perpendicular to the level surface. Because this happens not just for one curve, but for all possible curves. So if you fix a point, you can figure out that every tangent to every curve is perpendicular to the normal vector. So it stands to reason that the gradient has to be pointing in the direction of the normal to the tangent plane. So if you followed this discussion, how do we find the equation for the tangent plane for a level surface? By the way, I don't have a watch today, so you guys have to let me know what time it is. What's that? It's what? So I have 7 minutes? Okay, cool. So to find the tangent plane at, let's say, ABC for the level surface, f of x, y, z equals to some constant, whatever, k, let's say, we use the gradient of f at the point ABC as the normal. That's the application of this example. The fact that the tangent to any curve through the point is perpendicular to the gradient must mean that the gradient is actually the normal vector. So, as an example of that, if I have f of x, y, z equals to x squared minus xy plus yz cubed, whatever, make your favorite function, I would never want to graph that. It's awful. I suppose it's equal to what? What's it equal to? 21, okay. I couldn't see that. I'm glad you could see it. It's good. So the gradient of f is equal to what? It's 2x minus y minus x plus z cubed. And what's the z derivative? 3yz squared. So you guys give me a point on the surface, and I can write down the equation of the tangent plane. What you guys got to tell me a point on the surface, though. 249. 249. I do not believe 249. Z cubed is too big. What's that? I heard you put a 0 in the z. What did you say? What was it? 4, 5, negative 3. Are you guessing or are you sure? Let's see, 4. You're guessing? Oh, I'm ignoring you then. Okay, so how about this? All right, I'm going to stop asking you guys questions. 2, 1. What's that do? So 2 and 1 puts what? 4 minus 2 is 2, right? And so we get z cubed is equal to 19. So I need to put the cube root of 19 here. Ooh. Not what I wanted. Okay, cube root of 19. And so what's the equation of the tangent plane at that point? If you followed this example. The equation of the tangent plane then is, well, first I have to figure out what's the gradient of f at that point, right? It's what? 2 minus 1, which is 1, minus 1 plus 19, apparently. Yeah, that's not too bad, 18. And then, apparently 3 times 19 to the 3/2 power. Okay, well, excuse me, 2/3 power. And so if you don't mind, I'm going to write it over here. The equation of the tangent plane then is 1 times x minus 2. Oh, wait a minute. Did I put x equal to 1? Oh, wait, don't let me get away with that, guys. I was thinking x equals to 1 and y is equal to 2. That's wrong. What should I have? Fix it. What should I have here? Try that again.
3.
Uh-huh.
2, 5, 4, 5, 0.
It's too late.
But it's so much better.
It's too late.
It's so much easier.
No, I am not changing the point mid-calculation. I refuse.
But it's so much easier.
18.
This is 18?
No, it's 17.
Because I'm subtracting 2.
Yeah, you
Okay, 17.
okay.
And I think that one was right. 3 times 19 to the, well, yeah, 19 to the 2/3. Okay, so we have 3 times x minus 2 plus 17 times y minus 1 plus 3 times the 19 to the 2/3 power times z minus the cube root of 19. That equals to 0 is the equation to the tangent plane of that level surface at the point. Yeah. Because the gradient has to be perpendicular to every single curve that goes through the point by this example. Right? Now, I have not proved for you these chain rules, have I? Not yet. So I'll probably do that tomorrow. And there's other kinds of chain rules we need to look at. Like, what if you have more than one independent variable? What if you have a function of u and v, and then there are chain rules upon chain rules upon chain rules upon chain rules we need to cover. But they're all pretty easy. You guys will get them. Thank you. Oh, and if tomorrow goes well, I think there's a pretty good chance we're taking Friday off. So, is that okay? All right. Okay. Yeah. Yes.